Hello everyone, myself Choudhari, Department of Chemistry, RBNB College, Sri Rampur. Today we are going to see the concept of vapor pressures of solutions of liquids in liquids from the topic solution. Now let us see first, consider a binary solution which contains two volatile liquids A1 and A2 respectively. Now, both these volatile liquids, if that are kept in a closed container, then both the liquids undergoes vaporization because both are volatile in nature. Then, at one stage, there exists an equilibrium between vapors and liquid state. Consider both these volatile components that are kept in a closed container. Both liquids A1 and A2 both are volatile in nature, so they undergoes vaporization and there exist vapors over the surface of liquid in a closed container, and at one stage there exists an equilibrium between vapors and liquid state of both the liquids, and hence there should be the relationship between the partial vapor pressures of both these liquids and their mole fractions. Now let us see, to consider that relationship, here we have to study one of the law that is called as Raoult's law. Now let us see what is that law. Now this law gives us the relationship between partial vapor pressures of the two volatile liquids and their mole fractions. Now consider what is the statement of this law. Here Raoult law states that partial vapor pressure of any volatile liquid is always equal to the vapor pressure of pure component multiplied by its mole fraction. In the solution. This is Raoult's law. Now consider explanation of this law. For our convenience, suppose A1 and A2 be the two volatile components or liquids that are having partial vapor pressures P1 and P2 respectively, and mole fraction of A1 that are X1 and mole fraction of X2 that are X2. And for A1 its pure vapor pressure is given by P01, and for A2 component in the solution its pure vapor pressure is given by P02. Now here according to this Raoult's law, what is this Raoult's law? It states that partial vapor pressure of any volatile liquid is always equal to the vapor pressure of that pure component, that is multiplied by its mole fraction, and so partial vapor pressure of A1 volatile component is equal to its vapor pressure is P01 into X1, and for second component A2, its partial vapor pressure in the solution, that is given by P2 is equal to its own pure vapor pressure, that is P02 into its mole fraction X2. Now, according to Dalton's law of partial pressures, we can write total pressure of the solution P is equal to partial vapor pressure of first component plus partial vapor pressure of second volatile component. And here we have P1 is equal to X1 into P01 and P2 is equal to X2 into P02. By using these values in above equation, we will get total pressure of the solution. So here P1 is equal to P01 into X1 plus P02 into X2. Now also we know that in any solution, whatever number of components are present, if we do the sum of mole fractions of all the component in the solution, that always equals unity. That means sum of mole fraction of all the components in the solution is always equal to 1. Now in our solution that we have considered, that is binary solution, that contains only two components A1 and A2 respectively, and their mole fractions are X1 and X2. So here we can have X1 plus X2 is equal to 1. And so we can write X1 is equal to 1 minus X2. Okay. Now by using this value of mole fraction of first component in the pressure equation, then we'll get here P is equal to P01 into 1 minus X2 plus P02 into X2. Now by solving this bracket, we will get P01 minus P01 into X2 plus P02 into X2. Now here in this equation, X2, these values are same. So take that as a common. Now here let us consider, we'll get P is equal to P01 plus X2 into bracket P02 minus P01, or we can write here P is equal to P01 plus P02 minus P01 into X2, and this is the required pressure of the solution, which is binary solution and which contains two volatile components A1 and A2. Now in this equation, P01 and P02, these are the vapor pressures of the pure components A1 and A2, and both these values are constant. And so if we plot the graph of pressure of the solution versus mole fraction of the second volatile component, then we'll get idea about the relationship between mole fractions of component A1 and A2 with their partial pressures. Now here consider plot. Consider this as the x-axis. On this x-axis consider vapor pressure of the solution. And consider here again duplicate x-axis, because we have two volatile components in the same solution, and this is plotted against mole fraction, that is plotted against mole fraction of the volatile components from the solution. Now here we know that for A1 component, its own vapor pressure is P01. Now here if we consider P01 at this position, then here we will get straight line that goes to 0. Now here this one is the P01, that is the vapor pressure of the first volatile component A1, and its mole fractions are X1 is equal to 1. X1 is equal to 1. And same time here mole fractions of the second component should be 0, Because here the partial vapor pressure of component A1 is in the working position, and so here as x1 is equal to 1, x2, that is mole fraction of the second volatile component, should be 0. Now as here vapor pressure of the first volatile component that decreases and that goes to the 0 value. Now here that mole fraction of the first volatile component should be 0. Now when x1 is equal to 0, we should have x2 is equal to 1, because in the same solution the sum of mole fractions of both the component, that is unity, and that is constant value. So here as x1 becomes 0, x2 should be 1. And so here if we consider opposite case, that means for second volatile component, that is A2, then here for A2 component, if we draw the plot, here suppose this one is the P02, that is vapor pressure of the pure volatile component. Now here what happens when that both the components are mixed, here vapor pressure of that A2 component decreases. At that time here value of x2, that means its mole fraction is 1. Now here vapor pressure of the A2 component decreases and that goes to the 0 value. That means here its mole fraction should be 0. And so here x2 is equal to 0 we will get, and at that time x1 is equal to 1. And here if we consider together both this curve and if we plot the graph, then we will get this line as a straight line. Now this straight line that tells us that this is for ideal solution. This is for ideal solution. And here this P1 goes to 0, that should show the partial vapor pressure of component A1, and this curve that should show the partial vapor pressure of the second volatile component, that is A2. And here we know that there is no any solution which is exactly ideal, because here we will get here total vapor pressure P is equal to P1 plus P2. But here exactly no any solution is found to be ideal solution. Why? Because when we are mixing components to form a solution, there exist some interactions. Now which interactions are existing in the solution? That interactions are solute interactions. Again solvent interactions. And also solute-solvent interactions are observed. Solute-solvent interactions are observed. Now we know that every chemical substance that is differ from each other. That means every substance have its own properties which are distinguished between them. Now here as we are saying that the solution is ideal according to Rolle's law, then here pressure is equal to P1 plus P2. That means in ideal solutions, the interactions of solute-solute, also that solvent-solvent interactions and solute-solvent interactions, that should be comparable or that should be exactly equal. Then only the solution is said to be ideal solution. But that is not possible. Why? Because here every component that is having different chemical properties and that behaves differently from each other. And so here these interactions should not be equal. And so let us consider there are two types of solutions. Now consider there are two types of solutions. First one is ideal solution and second one is non-ideal solution. Now here we will see what is meant by ideal solution and what is meant by non-ideal solution. And second here non-ideal solution. Now here ideal solution means that is according to Rolle's law, That means here first point we'll consider here ideal solution obeys Raoult's law. What is that Raoult's law? Raoult's law means here partial vapor pressure of any volatile component is equal to the product of vapor pressure of pure component into its mole fraction. And here for binary solution containing A1 and A2 component, here that partial vapor pressures are given by P1 is equal to P01 into X1, and for A2 component P02 into X2. This is according to Raoult's law, and the solution which obeys Raoult's law, that should have this equation, should be satisfied that solutions. Now here consider. Now if both the solutions are ideal in nature, then whenever we are considering both the volatile components to form ideal solutions, we are mixing that components together. During the mixing of that components, there should not be any evolution or absorption of heat. That means here enthalpy change of mixing of that component to form ideal solution, that should be 0 for ideal solution. Now here consider third point. Now here according to Raoult's law, whatever that volatile components are mixed together, whatever their volumes are present initially, when they are mixed together to form an ideal solution, then here initial and final volumes of the solutions remains exactly constant. That means here delta V mixing for the ideal solution, that is also 0. Now here let us consider for ideal solution, the interactions. Which interactions? Solute interactions that exactly equal to solvent interactions, and that are also equal to solute solvent interactions. For ideal solutions, all the interactions, which interactions? Solute interactions, that means there exists a force of attraction between solute and solute particles. There exists a force of attraction between solvent and solvent particles, and also there exists a force of attraction between solute and solvent particles. All that attractive forces remains constant, or that remains same within these three interactions within the same solution, then that solution behaves as an ideal solution. And here last point we have to consider for ideal solution, vapor pressure of ideal solution that lies between vapor pressure of volatile components. This is very important. Vapor pressure of ideal solution that lies between vapor pressure of the components from which that ideal solution is formed. And here if we observe these points, then here there is no any solution exist which can satisfy all these points. Then here we have to see non-ideal solution. But here some examples are there which nearly goes to the ideal solution. For example, if we consider benzene solution in toluene solution, benzene and toluene, if they are mixed together, then they satisfy some conditions, and so they goes to the nearly ideal solution. Now here let us consider for non-ideal solution. Now here, as according to Raoult's law, that partial vapor pressures are equal to the product of vapor pressure of the pure component into their mole fractions, then here for non-ideal solutions we have P1 is not equal to P01 into X1, and P2 is not equal to P02 into X2 for both the volatile components in the solution. That means that non-ideal solution do not obey Raoult's law. Non-ideal solution do not obey Raoult's law. Also here whatever that delta H mixing, that means enthalpy of mixing of two volatile components, during that mixing either heat is absorbed or either heat is evolved. And so here in non-ideal solution, that delta H mixing, that does not equal to 0. And also when two volatile components are mixed together, then the volume of the solution always that does not remains constant, and so for non-ideal solution delta V mixing, that is also not equal to 0. And here whatever the interactions are there, which interactions? Solute-solute interactions, solvent-solvent interactions and solute-solvent interactions, that also vary from each other. That means here solute interactions that do not equal to solvent-solvent interactions, and also that not equal to solute-solvent interactions. And so such type of solutions are said to be non-ideal solution. That means in one sentence we can say that ideal solutions are exactly opposite to the non-ideal solution. And here why these interactions are different? Because here every substance that is having different chemical properties that behaves differently from each other, and so there should exist force of attraction, and that forces of attraction, their magnitudes should be different. And so here these interactions are not comparable to each other, that are not equal to each other, then such type of solutions are said to be non-ideal solution. Now here we are saying that here partial vapor pressures that are not equal to this product. Then here we can say for non-ideal solution either this P1 is greater than P01 into X1 and P2 that is also greater than P0 to X1, or here we can also say that this P1 that should be less than P01 into X1, or here P2 is that should be less than P02 into X2. That means here both these conditions can be observed for non-ideal type of solution, and so that non-ideal solution shows two types of deviations. Now let us see what are that two types of deviations. Two types of deviations observed in case of non-ideal solutions, that are positive deviation and negative deviation. Now let us see how that partial vapor pressures of two volatile components that are different. Now let us see two types of deviations. First one, positive deviation. Now here positive deviation is observed. Now here when this condition occurs in the solution, when solute solvent interactions are weaker than solute-solute interactions and solvent-solvent molecule interactions, or we can say that when solute-solvent interactions are less than solute-solute interactions and solvent-solvent interactions, then such type of solutions are said to be showing positive deviation. Now let us plot the graph for positive deviation. Now here consider the graph of vapor pressure versus mole fraction of volatile component in the solution. Now suppose that vapor pressure is considered on x-axis. Now here we have to consider duplicate axis because two volatile components are present in the same solution. These are plotted against their mole fractions in the solution. Mole fraction. Now here We know that according to Rolle's law, when here we are plotting that P01, suppose here P01, that is vapor pressure of pure component A1. Now here, as this vapor pressure decreases and that falls exactly 0, then here initially its mole fraction are x1 and that is equal to 1. At that time x2 should be 0. Here when this vapor pressure of pure component A1 that falls and that goes to the 0 value, at that time here mole fraction x1 should be 0 and x2 mole fraction of second component, that value becomes 1. Now this is for ideal type of solution. Now here in case of positive deviation, here for that first component the graph observed is like this. Straight line is not obtained. Here curve is obtained and which is above the straight line for the ideal solution. Now here if we consider P02 be the vapor pressure of pure component A2. Now here when this, if we consider for ideal solution, then here straight line is obtained. Now here for positive deviation, it is observed that here we will get a curve without obtaining the straight line. Now here this line or this curve is obtained for partial vapor pressure of component A1 and this is for partial vapor pressure of component A2 in the binary solution. And here for ideal solution, so here we can't get this straight line, so here we can consider that as a dotted line. That means that is the expected straight lines for the ideal solution. But in positive deviations the curves are obtained and that are above the straight lines, and so here dotted lines are considered. Now if we consider for total solution, then here expected is the straight line for the ideal solution, but here expected straight line is not obtained and here also we will get the curve, and that indicates the solution is non-ideal solution. And here the total pressure of the solution is P1 plus P2, or that is greater than P1 plus P2. Here as the solution is non-ideal solution, here total pressure should be greater than sum of partial pressures of two components. Now here when P1, whatever that vapor pressure, partial vapor pressure of component P1, that is equal to P01, that is equal to P01, and this is possible when x1 is equal to 1 and x2 is equal to 0. Now here when this P1 that falls to 0, P1 that falls to 0, then that value P1 is equal to 0, then here x1 should be 0 and x2 should be 1, and this is called as positive deviation. Now if we consider for second volatile component, its partial vapor pressure is P2, and when P2 is equal to P02, then here x2 is equal to 1 and x1 should be 0, and when this P02 that falls 0, then here x2 should be 0 and x1 should equal to 1. But here for positive deviation, here straight line is not obtained, here curves are obtained for the partial vapor pressures of both the component, and this shows that these solutions are non-ideal solutions. And here one thing is important, here this P1 that is greater than P01 into x1. This is for positive deviation, and also for P2 P2 is also greater than P02 into X2. This condition is for non-ideal solution which shows positive deviation. Now here exactly opposite case is observed for negative deviations. Now let us consider what are the conditions for negative deviation in the same solution which behaves as a non-ideal solution. Now again here consider second type, negative deviation for non-ideal solution. Now here when negative deviation is observed, there are three types of interactions. Which interactions? Solute interactions, solvent interactions present in the solution, and when both these interactions are stronger than solute solvent interactions, when the interactions, which interactions? Solute solvent interactions are stronger. These are stronger, or we can say that they are greater than the solute interactions. That means here attractive forces between solute and solvent that having maximum extent, then here solute attractions and also solvent attractions. When this condition is observed in the solution, then that solution is non-ideal solution, but that shows negative deviation. Now how that we'll see by graphical representation. Now here again we have to plot the graph of vapor pressure versus mole fraction of volatile component present in the solution. Now here suppose this is the x-axis and here vapor pressure is considered on x-axis. Now here we have to consider duplicate axis. Why this is? Because the solution consists of two volatile components. Now here consider here again P01 and here P02. For ideal solution, a straight line is expected. This is for ideal solution. But here when negative deviation is observed, here P01 that falls to 0. Here initially x1 is equal to 1 and finally x1 is equal to 0 value is observed, and same time x2 becomes 1 and here initially x2 should be 0. Now this condition, these straight lines are for ideal solution. Now when solution behaves or shows negative deviation, then here the curve obtained for this partial pressure of the first component P1 that exactly lies below the straight line for the ideal solution. Now this curve is for the A1 component in the solution, which solution is non-ideal solution and which shows negative deviation. This straight line observed or that is expected for ideal solution. Now here we will get curve for second volatile component. This curve is for partial pressure of the second volatile component, and here for total pressure of component we will get here the curve which lies exactly below the straight line expected for ideal solutions. That means here we can say that when negative deviations are observed, then here partial pressures are lower than expected values. Partial pressures of both the components that are lower when that are whatever that expected values are there, that are showing straight lines, then solution should be ideal solutions, and here solution behaves as a non-ideal solution. This curve is for non-ideal ideal solution and the solution which shows negative deviation. And from this graph we can say that here whatever that solute solvent interactions are there that are stronger than solute interactions and solvent interactions, and such type of solutions are non-ideal solutions but which shows negative deviation. So let us stop here. Thank you.